Our next speaker is Binggang Qu. I hope I pronounced.
I heard that Qu is a very bad word in Portuguese.
Portuguese, yes, indeed.
So,
from Peking University, and he will talk about string polytopes and Arakelov geometry on flag varieties over function fields.
okay, so this is a joint work with Yang Yu Fan, Yang Yu, and Wenbin Luo. Okay, so let's say over the field of complex numbers be a projective smooth curve. And E be a vector bundle on this curve C. And let's say it has a harder Narsimhan filtration like this, like E0, E1, ER. Okay. This is the canonical filtration that characterizes the stability of E. Okay, now from this data, you can cook up a discrete measure. Let delta E be this measure. Here, this mu of the pieces are just the slope, the successive slopes of the pieces of this filtration. Because you can have, because it can happen that the pieces can have rank greater than 1, so you want to put right multiplicity onto this. This is a Dirac at this point. This is a number. This is the slope of the piece, and you divide to make it to make the mass is 1. Okay, now you can, this might be a bad analogy, but you can consider this data as the eigenvalue of this vector bundle E. You know, I mean, just consider this as something, some spectral object. Okay. And then here we want to study flag varieties over function fields. So let G be a connected reductive group over a complex field, and P is a parabolic subgroup, and let lambda be a character of P that is strictly anti-dominant. Okay, and F be a G bundle on the curve C. So now you can have this, so like F over C. Basically, like every fiber will look like G, but the isomorphism is not canonical. And you can modulo P. Now every fiber will look like a G mod P, which is hence the name. This is like a flag bundle, over the curve. You call this guy pi. And with this character, you can cook the associated bundle construction, L lambda. You just do the associated bundle construction. Now this guy will be a line bundle on this guy, and the strictly anti-dominant is to make sure that this line bundle is vertically ample. Okay. Question? what is the limit distribution of eigenvalues of push forward of this guy? Like here, let me explain this notation. So for each n, you can first self-power n times to get this L lambda tensor n is like a line bundle here. And then you push forward, it will become this guy. This guy is a vector bundle on C. And you can ask its eigenvalues. Because here, like every vector bundle, you can associate with such a discrete measure. Now you do this for each n. You push forward to them, and you get a vector bundle. You cook up this distribution, this measure that describes the distribution of eigenvalues. And here, this little Tn is the follows. It's an operator on the space of measures such that Tn mu is such that the integration of x, f of x, with respect to T mu is just so basically it's just pulling back the measure by the multiplication map by 1 over n. Because you have to do this little tweak, otherwise this measure will just go to infinity and it is not interesting. You have to divide by n, you will get something more interesting. Okay, question. So here you see we are asking some asymptotic distribution of eigenvalues that looks like a wire law. This is some wire law. Okay. And to answer this thing, we need to use string polytopes, some convex geometry. So basically, the representation series, they could construct from this data, a polytope. This guy is inside some power of real space, together with a map to a much smaller polytope. This guy is inside the real, like the characters group tensor with R. So basically, I will not give you the definition, but basically, this guy parameterizes a certain selection of eigenvectors of the action of T, the torus of the group, acting on rational points in this guy characterizes eigenvectors, one particular selection of eigenvectors, the so-called dual canonical basis of Kashiwala. I want to mention this because Kashiwala was awarded the Nobel Prize, yesterday. Yeah. So, and this guy, the rational points in this guy parameterizes eigenvalues. Values of the same thing. So of course you have a map, right? Eigenvectors to its eigenvalue. Okay. But this polytope is much smaller. You can see from this, right? The dimension of torus is much smaller. Okay. Now from these polytopes, for such a G bundle F, we can do this thing. Let FQ be the canonical reduction of F to Q. So basically, you already did the same thing in the vector bundle case, because if you think about it, choosing a filtration of vector bond of the vector bundle is if you consider a vector bundle as GLN bundles, then choosing such a filtration is like choose a reduction from the frame bundle of E to some parabolic. And the thing, what's cool is that even in the world of principal bundles, you also have this canonical reduction, or like Hadron-Simhan reduction. Yeah, call it whatever you want. This is uniquely determined and exists and unique associated to F that characterizes the positivity of F. And if you have this reduction, now remember this guy is now a Q bundle. It is a Q bundle. So it just induces such a degree map from the character group of Q to Z by sending lambda to, I have to cheat a little bit, again, you do the associated bundle construction, Q, K lambda. Here, because lambda is a character of Q, right? So you can Q act on this field of K by lambda, and then you do this associated bundle. This will be a line bundle on the curve C. You take degree to get a number. Right? It's a very natural thing. What's cool is this function, although it is only defined on xq, remember not xt. Xq is much smaller than xt, but it can be canonically extended to xt. If you allow rational coefficient. Yeah. So I will also call this guy degree fq. And you do the compose. Let F be the composition of these two arrows. Now the theorem is this measure, this limit measure, this wear law thing, is equal to the push forward of the Lebesgue measure. Because here this guy lives in some real space. You have Lebesgue measure, right? And you just use this mysterious F to push forward the Lebesgue measure. You will get the limit distribution of this bunch of vector bundles. Okay. Okay, cool. So then, why do we care about such a thing? Like, what does this thing to do with arithmetic, to do Arakelov theory? So it's in fact very, very related. They are very related. So Arakelov geometry. So let me copy the graph again. Just Mescal X is the flag bundle over C. You let K, this big K, to be the function field of C, and now you have the generic fiber here, L lambda. So Farbod mentioned that height are just the intersection number, but he never did give a definition. So I will write down the definition for Farbod. So you have this k-bar points of X to, here is function field. So the value are really just rational numbers. And the construction is super easy. So you have a k-bar point here. You take the Zariski closure in this big X. You will get something one-dimensional, right? And you intersect with L lambda, which is something codimensional one. You will get a number, and you divide by the degree of X. You get this. This is a very simple construction, and this is the function field analog of a height function in Diophantine geometry. You can already see from here that this is this sort of height function. You know, the function field height function is much easier than the number field case, and which is it really is. For example, like for the function field height function, the ABC conjecture is known like 20 years ago. So It's supposed to be easy. It is some real world where like number field cases are like this is like dream world, and number field are like real world. So yeah, let's now dreaming. Okay, now given such a thing, you can cook up a so-called height filtration. You consider this ZT, this set to be, you collect all the points whose height are smaller than t, and you take a Zariski closure. So like now for every real number, you have a associated closed subset of X. Okay. Now our theorem, we could compute ZT for every t in this context for this height function. Is given by successively deleting Schubert cells CW at critical points zeta W. Let me explain. Like W is some double coset in W modulo WP modulo WQ. And zeta W is degree FQ W lambda. Y group can act on on XT, so you can have this. And here is the thing. So basically, let me draw this. This is a real number. This is a real axis. This is the biggest among all these guys. When you apply the longest wire element here, and the smallest will be the one with ID, with W equal to ID, and you will have some things. These numbers, and for t is here. ZT is just the whole X. It's just the whole X. Because you can see like when t is very big, this set will just be the whole X. And now you let t, you decrease t. When it meets this guy, you drop CW. Where do I will write here. Like CW is FQ QWP P, and then you look at the generic fiber. It's just some abstract way of stating the corresponding Schubert cells. I mean, you know what it means by Schubert cells indexed by wild cosets. It's just here it's just the thing. So basically, here you have the whole X, and you let t drop. Each time t meets these critical points, these critical values, you drop, you delete one Schubert cell. In this sense, that this height filtration really is just coincide with the Brouillard decomposition. Okay. Now, let me end with, because I said that this is like the dream world, right? But we have to live in the actual world, the number field case. So for number field case, we don't know how to prove it, but we have good guess, and the guess will be like this ZT, this sort of height filtration. They will be given as the filtration mentioned in the last talk, that they will be the filtration of flag varieties indexed by Matroids. Things are very different there, because here you see you have a choice by stability. You have the choice of one parabolic, or let's say Borel sort of thing. But in number field case, you will not have such a choice. In fact, every Borel will be the same. So when you do the stratification thing, you will have to do the Brouillard decomposition for every Borel, and then take all the intersection to get the finest stratification, which is exactly the one that indexed by Matroids. Yeah, I mean, that is our guess. We don't know how to prove it. It is the case for projective space, but for Grassmannian, we don't know how to prove it yet. Okay, I want to thank the organizers for having me here. Thank the audience for the attention, and yeah, thank you.